So I'm going to solve some problems now from chapter 6. And in the first problem here, we have a nozzle, and the nozzle is has some flow going through it, and the flow is initially at a density of 2.21, velocity of 40 meters per second, and an inlet area of 90 centimeters squared. Comes out, we have the density and velocity there. The question is asking what is the mass flow rate, assuming that this is a steady flow system. So one assumption is that we have a steady flow system. Okay. Now, what's the first thing that we can do here? Well, to find the mass flow rate through this system, so let's find mass flow rate first. So the mass flow rate through this system is we're going to use our mass flow rate equation, which is rho of our fluid at the inlet times area, cross-sectional area at the inlet, times the average velocity. All of these are given at our inlet condition. Okay, so our density is 2.21 kg per meter cubed. Our area is 90 centimeters squared. And I'm going to go ahead and convert this centimeter squared to meters squared. And our velocity here is 40 meters per second. So let's look at the units here. So we have meters, 3 meters here. That cancels out with this. The centimeters cancel out. And we're left with kilograms per second. And if we carry this calculation out, we'll get a value of 0.796 kilograms per second. Okay, so here's our answer. That's what the mass flow rate is through this nozzle. Now let's talk a little bit about it. Now, what can we expect the mass flow rate at the exit of this nozzle to be? This is just a side note, but since we don't have any other mass flow rates coming in, so we don't have these, and there's no accumulation, typically in a nozzle we're not going to have any accumulation of mass, and using a nozzle we're usually going to have steady flow operations. We can say that the sum of the mass flow rates in equals to the sum of the mass flow rates out. And in this case, since we only have one inlet and one exit, mass flow rate coming in equals mass flow rate coming out. Okay? So that's an assumption that we're going to be making for this problem, and it's a valid assumption for a nozzle type problem. Okay? The next question is we want to find the, or let me use another color pencil here. The next question is we want to find the exit area. So the exit area we can calculate using our mass flow rate. So remember, we just stated that mass flow rate in is equal to mass flow rate exiting. Since this is a steady flow system with only one inlet and one exit, and so mass flow rate exit is going to be equal to rho at the exit times V at the exit times A at the exit. And this is all equal to a value that we just calculated, 0.796 kg per second, since the inlet equals the exit density. Now the exit density is given, so this is 0.762 kilograms per second. Exit velocity is also given, 180 meters per second. And our exit area is given, or is not given, that's what we're trying to find, and this is all equal to 0.796 kg per second. So if we calculate this, this would come out to be exit area is equal to 0.0058 meters squared, and that's equal to 58 centimeters squared. So that would be our exit area here. Okay, so that it takes care of that problem, and that really just demonstrated conservation of mass for a steady flow system. That was pretty straightforward problem, and you guys can watch it over again if you have any questions. But what I'm going to move on to now, let's look at a nozzle problem again, where we have this time steam. So now we have steam or water. We can say water or steam. And in this problem, again, we have a steady flow system. So this is steady flow. Since we're dealing with a nozzle, this is a acceptable assumption for us to make. So we have 400 degrees Celsius, 800 kilopascals, and coming in at 10 meters per second here. Exiting, we have steam at 300 degrees Celsius, pressure of 200 kilopascals, and we have some heat loss through this nozzle, which is a value of 25 kilowatts. We know that the area, this inlet area here, is 800 centimeters squared also. What we are interested in, so let's find exit velocity, and let's also find the volumetric flow rate. Okay, so where do we start in this problem? Well, what I would like to do is I would like to just go ahead and start with writing down what do we know. What do we know? Well, we know at point 1 that the temperature is 400 Celsius and the pressure is 800 kilopascals. And again, I encourage you guys to try to solve this on your own, okay? You know what the problem statement says now. Try to solve it and try to get the answer on your own, and then see how I do it after you've paused it and check how I solve this particular problem. Alright, at point 2, we have a temperature of 300 degrees Celsius and a pressure of 200 kilopascals. So that's pretty much all we know. We also know that the area at the inlet is 800 centimeters squared, and we know the velocity. Well, to me, if we're trying to find the exit velocity, let's see what we need. We can write down let's think about what's in our toolbox right now and what we've talked about in the course. So let's write it down here. So our toolbox, so far we've talked about conservation of energy, right? And conservation of mass. These are our two things that we know right now. So this is what we have. And you can start at any one of these, I suppose, that you like. But since I wrote it first, let's write down the conservation of energy. our conservation of energy is the first law. So we have Q dot minus W dot is equal to, for an open system, this is going to be the mass flow rate times H exiting times Hn. And since this is a nozzle, I'm going to go ahead and consider the kinetic energies also. So we have kinetic energy of the exit minus kinetic energy of the inlet. Well, there's not any boundary work done here, right? I mean, we just don't have any done since it's a nozzle system here, so we can cancel that term. Okay, so we have heat transfer. And heat transfer out of a system, when we use our typical sign convention, is going to be negative. So we have negative 25,000 kilowatts. Or watts, I'm sorry. Now, keep in mind, I'm writing watts because I have this little circle here, this little dot. M dot signifies that it's a rate, okay? So it's going to be per unit time. So the mass flow rate here, mass flow rate, we don't know. We don't know the exit or the enthalpies. And what about the kinetic energies? Do we know those? Well, we don't know the exit kinetic energy. And we do know the inlet kinetic energy. So this is 10 squared over 2. Okay. So this helps us to identify what it is that we know and what we don't know. So what we need to find are the enthalpies at the exit and the inlet. And while we're at it, let's just find those for now. Okay. So the enthalpy that we have here, let me get the property tables. Hopefully I finally figured this out so that you guys can see the property tables. If not, I apologize. I'll do my best so that you can see it. If not, we can go over it some more in class. Now for our first condition, let's look here. So our first condition is 400 degrees Celsius, 800 kilopascals. Is that steam or is that a saturated vapor or saturated liquid? So let's look at the pressure tables. Pressure table, let's look at 800 kilopascals. Here we go, 800 kilopascals. So anything above 170.41 degrees Celsius is going to be a superheated vapor. And sure enough, we have 400 degrees Celsius, so we know we have a superheated vapor. We'll go to our tables here at 8.8 megapascals, which is what we have, and a temperature of 400 degrees Celsius. We can say that our specific volume is, let's see, so let me write this down. Our specific volume here is 0.38429 meters cubed per kilogram. Then let's also write down our enthalpy since we need it here at the inlet. Our enthalpy, let's see which column that is. Let's see, it's the third column. So the third column is 3267.7 kilojoules per kilogram. Okay? Alright, we got that. So now let's look at what we need at point 2. So let's start this process again. Let's look at 200 kilo. Let's go to our pressure table. 200 kilopascals. Anything above 120.21 here is going to be a superheated vapor. So yep, we're above 120.21, so we're in a superheated vapor. Tables. Let's go to point 2 and let's go to 300 degrees Celsius. So at 300 degrees Celsius, our specific volume is 1.31623, and this is meters cubed per kilogram. And our enthalpy at the exit here is going to be equal to, let's see, 300 3072.1, and keep in mind this is kilojoules per kilogram. Okay, so let me put this up now. So let's put those values into here. Okay, so we have minus 25,000, and that's equal to the mass flow rate, which we still don't have. Let's find what that is really quickly here. So mass flow rate is rho, and let's go ahead and use it since we have the area of the inlet. Let's go rho I AI VI, all at the inlet here. Now remember, density can be calculated or substituted for the 1 over the specific volume. So our specific volume here is 0.38429. Our area at the inlet is 800 centimeters squared. So 800 centimeters squared, and I'm going to go ahead and convert that to meters squared. So that's 1 over 100, 1 meter, 100 centimeters squared. And the velocity at the inlet is 10. Okay, so we have put this in our calculator here, and we'll get the mass flow rate for our system is 2.082 kilograms per second. And remember, this is a steady operating system, so the mass flow rate, and there's no other inputs in our nozzle, so we don't have anything else coming in. So our mass flow rate is constant, or it's conserved. So what's coming in is coming out. That'd be the same value at the exit. So regardless of where we take this mass flow rate is the same inlet or exit. So we have 25,000 watts times 2.082. We know the enthalpy at our exit is 3072.1 minus the enthalpy at our inlet, which is 3267.7. Okay, and that is plus V exit squared over 2 minus 100 over 2. Okay, so if we solve for, in this equation, V exit, we would get a value of 606 meters per second. And that is our exit velocity. Yeah, because we have one equation, one unknown, so we can solve for that. Let's now find our volumetric flow rate. So let's find volumetric flow rate. Okay, so knowing that we have conservation of mass, there's nothing else coming in, it's a steady flow system, we can say sum of the mass flow rates coming in equals sum of the mass flow rates coming out. We only have one inlet, we have only one exit, so mass flow rate in equals mass flow rate out. We can say that the density at the inlet, area at the inlet, velocity at the inlet equals to density at the exit, area at the exit, velocity at the exit. Now keep in mind, we're trying to find the volumetric flow rate, which is the combination of these two terms. A times V is volumetric flow rate. So we'll rewrite this as density at the inlet times volumetric flow rate at the inlet is equal to density at the exit times volumetric flow rate at the exit. Now we're trying to find volumetric flow rate at the exit, so this is what we're wanting to find. And keep in mind, if density is the same, then volumetric flow rate is the same. But now we know that volumetric flow rate is not this. I mean that densities are not the same because our specific volumes are different. So we can't say that the volumetric flow rate in is the same as the volumetric flow rate out because densities are in fact changing through this nozzle. So the density at the inlet we determined is 1 divided by 0.38429, which is 1 over the specific volume, times velocity at the inlet, which we know is 10, or volumetric flow rate at the inlet, which we can determine using our area, which is 800 centimeters squared, and I'll convert that 1 over 100 squared times 10, which is our velocity at the inlet, and all of this is equal to the density at the exit, which is 1 over our specific volume, 1.31623, density times area, which we are trying to find. Let's see, do we know the area at the exit here? We don't know it, but we do know we are trying to find this. So there you go. One equation, one unknown, volumetric flow rate at the exit. If we solve for this, it comes out to be 2.74 meters cubed per second. So there you go. So we solved 2 problems, quite involving here, and them having to do with a nozzle, both steady flow problems, using the first law of thermodynamics in each case. So I hope you guys got a good experience with those. We'll keep practicing these as we go along here, and we'll do a couple more problems in the next lecture.